Okay, now we will reconsider some aspects of last time. Then I would like to open MATLAB to show you how easy it is to solve or to apply the concepts which I told you until now. We will see, nevertheless, at the end of the simulations, a non-convex optimization problem in which, you remember, the open problem was to determine the order of the polynomial. But let me recap the last part of the lecture in order to restart with the formulation of the open problems, to go in depth on these minimax problems and to apply. And then this topic here, go ahead with, you remember I told you another family of regressors, trigonometric regressor I would like to consider in order to compare a little bit, to show you that not only the polynomial is possible, to have the feeling that basically any kind of functions, let me say, or even though it's not totally correct to say any kind of functions, but in the sense, in the wide sense, nevertheless can be considered valid. This sense, this sentence. Theoretically, I can also mix different function in order to approximate, in order to fit data to build a non-parametric model. But anyway, I don't want to go in depth on these mathematical aspects because the course is more oriented, in implementation, I would like to say. It's in a course for everybody. Okay, let me switch, if I'm able to do now. Why does it work? Okay, let me switch the presentation. The presentation is always the same until now, and we will see once we will finish with we complete. Excuse me. The lecture, I will upload all the material. Okay, let me reconsider a few words, starting from here. Do you remember this? 1 second. Now, I'm a little bit. Yeah. Do you remember this? Again, n is given. Could be 2, could be 3, could be 4, is given at this moment. Of course, n, the order of the polynomial, in general, I should say, we will see later, the number of coefficients. Also, in this case, n is connected with the number of coefficients of the regressor. Regressor means a function which or the functions, but let me say function or family of functions, polynomial in this case, which I would like to use to fit the data, to generate this non-parametric model. The parameters of the non-parametric model, do you remember, I clarify also this mismatch in the wording, because remember the non-parametric model means that the parameter are not directly connected with the physics of the system. I mean, if you look here, the parameter A0, if you think about our system, is in the what we want to approximate is the flux of the motor over the versus the current. We have a current up to n. This means A0 is Weber divided carry up to n. This means physically no particular meaning. Just to recall. Again, n is given, n represents also the number of or reflects the number of coefficients, because the number of coefficients are n plus 1. This means in general, we will see later when we'll consider their trigonometric functions, that the parameter to be optimized is the number of coefficients, which in this particular case are related, easily related with the order of the polynomial. The number of coefficients equals are n plus 1, no? Is n plus 1. The number of coefficients equals, let me say, n plus 1. In any case, if n is given, you remember the concept. I can say that I can split what is known. Here is a problem. I don't have also. No, better. I can split what I know. This matrix here is the exploration matrix because it's built using the exploration variable. Exploration is easy to remember because using the current or using the variable in the domain, we explore the phenomenon. Remember in the picture, with 1 ampere, we have, I don't remember what, 38 Weber, something like that. With 2 ampere, we obtain another value, and so on. Now, I explore the phenomenology, let me say, or the phenomenon, using the input x. It doesn't matter if it's ampere or the time. Anyway, I explore with the matrix, with the variable x, my phenomenon. And then, of course, in this frame, I explained last time or many times, we have a matrix. The name is exploration matrix. Of course, in any case, it's also clear that the vector of the measurements, y1, y2, ym, is also known. Now, these expressions, or this expression in terms of matrix, represent the constraint, the condition. I mean, I would like to calculate a0, a1, an, and it's, what I know is totally split with respect to what I don't know. I mean, what I don't know is localized in this vector. This expression represents our condition. Condition means I consider this family of functions and is given. We will see that also this could be object of our optimization. The number of coefficients we will see today. Also the family and so on. The family we will see a little bit next week, I think. But the idea is to have an optimization of everything. Now, the problem is convex. You remember, is convex if, this is also a condition, if in the constraints, exactly the equations which I have here, I can separate what I know with what I don't know. What meaning this? If n is also an object to be optimized, an element to be optimized, I cannot say that I can split what I know with what I don't know. Why that? Because in the matrix, inside here, we mix what I know, which is x1, x2, x3, xm, and what I don't know. And if n must be found, no, it's not given. At this moment, let me consider n, which is given. This means the constraints of the conditions are exactly condition in which I can separate what I know with what I don't know. The other conditions which I told you in order to have a convex problem is a convex cost function. Now, do you remember last time I told you this? I received a question per email. I would like to clarify. Therefore, I started from here. Look at this cost function, the error. Just let me say, the linear error. Linear with respect to theta. If I would like, I mean, you remember this error is the difference between what the measurement vector, which consists of y1, y2, ym, is, and the fitting vector, which is a vector which I don't know. I mean, y hat, this expression, let me move this. This vector here, y hat, is a fitting vector, is basically is the right part of the equation and represent, let me go, why doesn't work? 1 second. Oh, now. And represent this point on the blue line, this point on the blue line, this point on the blue line, and excuse me, I don't have the mouse today. This point, and so on, which I don't know because I have to calculate through the calculation of A0, A1, AN. This point here, and so on, are unknown at the beginning. Now, I receive a question that therefore I would like to clarify this. If the cost function to be optimized, here at the end of the slide, we cannot see the last part to be optimized. Is the linear function of theta. This means a linear function of the error, like here. We don't have solution. I receive an email to this question here. Let me switch on to clarify this concept here, because nevertheless is important in my opinion. It is important because today I would like to go in depth on this minimax problem, and then I would like also to simulate a non-convex optimization problem, to simulate in the sense to explain a little bit this non-convex optimization problem, in which we will calculate an optimum for n and for the vector theta, both. I told you that if I include n in the optimization problem, the problem is not convex. Because here the constraint, even though I can consider, we will see together, I can consider a convex optimization and a convex function, but if the constraint is not a suitable constraint, I mean, if I cannot separate, I cannot speak about a convex optimization problem. We have more than one optimum in this sense. Let me clarify this before going ahead. Okay, let me switch on the lateral camera now. With Zoom is always a problem to understand what I have to do. I hope you can see me. Look here. Why we don't have solution? This is exactly what I would like to minimize, not the error, just the error, in order to understand how important is the convexity of the cost function. This is the error in our case, formally written in terms of y, which I know, minus x, which I know. Theta is our unknown formally, because here the problem is quite complex in the sense theta is in a vector, x in a vector, y is in a vector. Let me do, in order to explain an easy example from high school. Y is equal 1 minus x multiply theta, in which x is known. I mean, I would like to find, if it is possible, the minimum of this expression with respect to theta. Therefore, I told you is a linear function with respect to theta. This means the error which I am considering as a cost function to be optimized is a linear error. Look, do you remember in high school, the derivative of this expression with respect to theta, I have to put equal 0, and if I do the derivative of this, I have x equal 0, but x is not 0. This means I don't find solution. Just to flesh out what I intend when I say if the cost function to be optimized is not a convex function, it happens that we don't have solution. This is an example in order to give you a feeling. Of course, mathematically should be clarified better. What happens if the cost function, for instance, is not linear, but not only is convex? Yeah, we have the minimum. Just to understand what I intend. What I intend. again here, if I have to minimize this is linear. We have something strange. We don't have any minimum because this function is a monotonic function. Yes, the derivative with respect to x. Just to recall your knowledge on the knowledge in high school. Again, in complementary classes, all students are admitted to attend the class. This means I understand the question from some students. So there's some students that don't remember exactly what I did. Here, from here is exactly gymnasium, no? Our high school. Here we have a minimum. We can see, because we have a convex function. This is a monotonic function, no solutions. Therefore, I told you last time, in this sense here, in this cost function, with respect to theta, in accordance with our notation, we don't have a solution because x is equal to 0, but x in our case is not 0. This is a contradiction, because this is a full column rank. I will come back to the concept of the full column rank. In any case, is nematic with values, but not 0, just to understand, to answer the question. Let me go ahead now quickly, but nevertheless, it's important also for the topic of today. Now we can understand, I hope, better. Let me switch. Why it doesn't work? Why not? Without mouse, it's difficult for me to... I don't know if you see now the presentation, difficult to understand where I am with the matter. I think you see the presentation. Yeah. Okay, let me come back. Yeah, you see the presentation. Therefore, last time I told you that if I try to optimize the linear error, this means in the function linearly depending on theta, we don't have solution, non-existent. Totally don't understand. It's a shame I don't have the mouse today. And this is difficult for me to manage this. Yeah. The solution does not exist. Even though I can consider the sum of the error, if I consider in an abstract form the error, if the cost function linear, keep in mind this. I can consider any variations of the error, linear, some, in any case, if it's linear, sum of all errors, one error, the maximal error, it doesn't matter what. If the cost function is linear, monotonically, I would like to say, linear, in the sense is linear, what I have here in this presentation, but in general, in a monotonic function, the solution does not exist. Why it doesn't work? Here, do you remember, if I am considering this cost function is the sum of the error square, this was the goal of the topic, I told you last time that we can find the solution. I don't want to repeat this boring calculation because the question was a little bit more conceptually. And if the cost function is convex, if the constraints are represented as in a split form, what I know and what I don't know, this condition here in the middle, in the left part, the derivative of the cost function, which is the least square in our lecture, with respect to theta, which I want to calculate, equals 0. In this case, the condition, which typically is necessary condition. You remember, I repeated also today with the high school knowledge, the derivative is a necessary condition. It's not enough in general, because I have to check the second derivative and so on to classify the minimum and maximum, but becomes sufficient if I know that in our optimization problem, if the optimization problem is convex. The conditions are two, and a convex function, cost function, and the constraint, which must be in this form in which I can recognize what I know with what I don't know. And in this also in this solution, what I know and what I don't know is reflected in this solution here at the end. Why that? Because we have this up to -1. Just recall us in our high school, how possible to say that I can isolate on the left part, you remember in high school, what I don't know, on the right part, what I know, and then I can explicit what I don't know as the function of what I know. Exactly here. No? Look, theta is what I know, or what I don't know, excuse me, on the left part. And on the right part is everything which I know. But this, of course, it works if I can split. But of course, in the concept of in our frame, the conditions are two. Okay, about SST, SSR, and SSE, I already told you that we can define the different figures of merit or cost functions. And if you remember, I try to classify it a little bit also. Yeah, let me tell from here to repeat the meaning of these indicators. SSE is our least square. This is basically yeah, an indicator which is more deterministic. I would like to say deterministic, because yi is our measurements, y hat is our approximating vector, Bowes vector. No, yi is a vector in the sense in this formulation is not represented in a vectorial form, but we can consider that I can organize the measurement in vectors. SSE, SSR, here in the lower part, is a statistical indicator, because we can see that y overline, do you remember, is the mean value of the measurements. This means we have an SSE, which is something, how possible to say, related to the deterministic indicator, and SSR is more related to statistical one. SST is something related to the variance, no? The variance of the measurement, because if you remember, it's exactly the variance multiplied by m-1. M is the number of measurements. SST is something like, it's proportional to the variance. The variance. Yeah. Do you remember I told you that in general, that here's a repetition or more in depth about that, about what I told you now. This sentence here, SST equal SSR plus SSE, is in a sentence which works. It works just if I have an infinite number of measurements, but can be considered also valid for. I mean, what is the meaning of an infinite number of measurements? No meaning. Infinite means m much larger than the number of coefficients. You remember last time I told you m much larger than n plus 1, but also much larger is in the wording, but can be considered as an approximation, of course, or an approximating equation. Of course, in the case of 2 points, it's just in a didactic approach, because we know that 2 points are something which that does not represent any anyway, at least in engineering fields in which the variables are continuous variables, the current is continuous variable. To have two measurements, of course, this is difficult to say that these two measurements represent the phenomenon. But anyway, didactically, assuming that this works, we can write in this form here, on the right, remember this, just divided by SST, and R squared is basically SSR divided SST, and this indicator, as R squared, which is SSR divided SST, could be considered as a possible indicator, but this R square has some drawbacks. We will see that typically we don't use this, or we use in particular situation. I mean, R square is always positive. This is not a drawback. It's between 0 and 1. This is not a drawback. We can see that is between 0 and 1 for SSE equals 0 when I fit all points. If SSE is equal 0, if I fit all points, as in the first approach here on the left part, we have the R square is equal 1. In case SSE equal SST, and this is the case I showed you last time, I showed you when basically I will consider the right part in which I will consider basically just the mean values. No? I can show you in more in general. Of course, is R square equals 0. Cannot be more than 1. Yeah, cannot be because this means how possible to say in any case SSE cannot be larger than SST because otherwise we have R square is positive, no? Square is positive because it's SST divided excuse me, SSR divided SST. Both are positive. We can see from here, no? Because it's the squared. This means it's clear that SSE cannot be larger than SST. Clear, no? SSE cannot be larger than SST. Otherwise, R square is not positive. R square is positive because it's the ratio between SSR, which is positive, and SST, which is positive. Cannot be, in any case, larger than 1. Why that? Yeah, because SSE divided SST is always positive. No? And SST, yeah, is always positive. This means cannot be larger than 1 also. The drawback of R square, we will see in 1 second, and then we will go ahead with MATLAB, that can be demonstrated. I don't have yet the demonstration, but it's not so difficult to intuitively also from this picture. That is a monotonic function with respect to n. This means if I want to optimize, and then this is the topic also today, with respect to n, R square is not a suitable cost function. The reason is that is monotonic. I insisted also today on the monotonicity of a function, of the cost function, which is not suitable. But of course, could be possible to use R square in case n is given. But this kind of problem, of course, it can occur. N is given. This means the regressor is given. Also, the number of coefficients of the regressor are given. But in general, at least in engineering fields, very often we need or we define the more general problem, in which we try to optimize everything. I will show you what I intend. Let me see if I forgot to say or to repeat everything. Yeah, left and right, R square equal 1. I will meet all points. This means, as I told you, SSE equals 0. SSE equals 0 because we can see from here probably a bit better. Where is? Yeah. When I meet all points, we have, if you look at the definition, that y, what's the problem? Here. Excuse me, I don't have the mouse. If I meet all points, means that y I hat is exactly yi. This means, of course, SSE is equal 0. We say, in this situation, exactly here, that we have the minimal deterministic error but the maximal statistic one. Why that? Because less than less than 0 SSE cannot be. Do you remember? Because it's positive. And SSE is related more to the deterministic error. And in this case, I mean, SST is always given, because depends of the measurements. If SSE is the minimal possible, SSR is the maximal one. Therefore, we read in the book, the case, the first approach is an approach in which we have the minimal deterministic error, but the maximal statistic one. And vice versa, the second approach. No? Because in this situation, we have R square equals 0 because SSE equal SST. I showed you before, I think. No? I mean, if I approximate everything with everything, I mean, if y hat equals for each I y over line, it's exactly, look at here, that SSE collapses in SST. If y hat for each I equal y over line, that is equals. This means we have such a situation in which we have now the maximal deterministic error, but the minimal statistic one. Now, this allows to conclude a little bit on this repetition, or let me say repetition, but in any case, to try to go in depth to introduce the lecture or the topic of today, because we can understand well that if I want, if n is given, yeah, I can of course consider this R square, let me say, as in a possible indicator in order to calculate the parameter theta. Of course, this can be done. I mean, I can try to, in this sense, to minimize R squared. But in general, we will see that we used another parameter because R square adjusted, as I told you last time, because typically the problem is more, at least in our fields, in the engineering field, is more articulated, includes also the number of coefficients, because with the number of coefficients, we can also choose the family. Let me see here. This, I think, I don't need to. The sentence is interesting here at the end. I try to explain. It is written that R squared can take on any value between 0 and 1. I already told you, I try to explain. And then there is a remark I would like to say. If the value is close to 1, in our case, the result, I would like to say, indicates that a large proportion of the variance is accounted, is fitted, I would like to say, by the model. No? There's a little bit this situation here, even though here is clearly on the left. No, the first approach is extreme, the situation, because we have just 2 points. No? This means, I have just the situation in which I meet all points, or I don't meet any points. But this is a little bit the meaning of this sentence. Of this sentence here. Then we have an example. Because SS is 0, no? In our case, or close to 0, no? If R square is close to 1. Isn't a good situation? This could be, I would like to comment. Typically, we don't like to obtain or to have R square equal 1 or close to 1. We don't like because did you see the sentence at the end of the slide? If we have a close to 1, this R is also called residual square. No? R square is also in some books called residual square. Close to 1, this means, let me see the case 1, so it's clear what I intend, that we trust totally the data. If I meet all points, or if I close to meet all points, here is written closer to 1. This means that we consider the measurements totally, let me say, we consider the measurements that reflect totally the phenomenology of our process. This means we trust totally the measurements. This practically is not a suitable situation because the problem of overfitting means that I will also include in my valid or possible valid model some noise, some errors. To trust to match the value of the measurement means to have an R square, this residual square, close to 1 or 1, which is not as suitable because the name of this phenomenon is overfitting. This means we consider also valid possible noise, possible error in the measurements. Yeah, I think this exactly the comment on this value on this yeah. Now, important that we conclude with OpenMATLAB. If I want to consider an optimization problem, a general optimization problem in which I will can optimize also the number of parameters, and I told you R square is not convex with the number of parameters. I didn't demonstrate, but if you just consider this example, we intuitively, in this case at least, we can see the meaning. I mean, from 0, we have for R square equals 0, increasing n. On the right part, we have n equals 0. As in a constant, the order of the polynomial is 0. No? We have just a constant. A constant is a mean value. The order of a constant in terms of polynomial is 0. Starting from 0, we have R square equals 0. If I have n equal 1, in this specific case in which we have just 2 points, I have R square equal 1. In this case, of course, we have just the 2 possibilities. But also here, we can see the monotonicity of R square with respect to n. With respect to n. In general, the optimization problem is not just related to data. I will show you the simulation now, but we have to consider also n. In this case, we modified the R square and we obtain R square adjusted, in which you multiply the ratio SSE divided SST by m minus 1 divided m minus p, in which p is exactly the number of the coefficients, which in this particular case, if the regress in a polynomial is n plus 1. Of course, we can also modify in different forms. We have also different indicators. I don't have time to tell you about different indicators. It is enough to get the concept, no? The idea to obtain a convex function as an indicator or cost function. We say in optimization cost function, because otherwise I cannot define an optimization problem. Do you remember the example of which I did exactly today from your high school? No? I cannot optimize. I cannot find the minimum of a line. I need a convex function. R square is not convex with respect to the order of the polynomial. This, yes, it is, or that can be seen. Why that? Because increasing n, this is the problem, no? increasing n, you remember I told you that R square increases from 0 to 1. Increases n, SSE will decrease. Do you remember this? SSE will decrease. But if you look at this correction factor, increase n SSE will decrease, but also the denominator, this denominator, m minus n minus 1 will decrease. I don't understand. 1 second. I don't have the mouse. Here. Because P will tend to M. This means it could find in a region in which the problem, or the convex function, the optimization problem is convex, or the convex, or the function to be optimized is convex. Because now it's not clear what happens, because as SSE decreases, the numerator decreases, but the denominator decreases too. This means we can find, very often we find, regions. I show you what I intend with the word region with the MATLAB, in which I can optimize everything. Theta and n. Why theta and n? Because the problem now can be formulated in this form here. I am looking for the minimum of R square adjusted. Why that? Because the idea is to obtain the minimum with respect to theta and the minimum to respect to n. Why that? Because in general, the minimum of R square, or in this particular case, the R square adjusted, represents somehow the minimum of SSR, because R square, so defined, reflect, or is basically SSR divided SST, in accordance with a sufficient number of measurements. And this is basically, let me say, our goal, because we give a priority to the statistical error. I remember I told you also this, because to minimize just the deterministic error, we will fall down in a situation, in this case, in an extreme situation, in which I fit all points. We fell down in this overfitting problem. This we don't want. This means a suitable way to proceed is to minimize SSR. In this modification, the most suitable form is to minimize R square adjusted with respect to n. Now, in this formulation here, we can see that to minimize R square adjusted in general, can be written in this form. I mean, the minimum of R square adjusted with respect to n, which is written here, but also the minimum of SSE with respect to theta. These two minimum basically represent somehow the minimum of the deterministic error, SSE, and the minimum of the stochastic one. This means we try to minimize both error in the sense. But this correspond a minimax problem. Why that? Because the minimum of SSE means the maximum of our R square adjusted, because the maximum is basically one. I mean, minimizing SSE, we tend to the maximum of, think about R square, if you don't want to consider this correction factor. let me now try with MATLAB. We are at the end here. Let me consider now the easy example in which I will minimize just SSE with respect to theta, and then we will see a more general problem, exactly what we have in the equation 2, which we try to consider the minimum with respect to theta, and the minimum for SSE is the minimum with respect to n of the whole expression. Let me think if I forgot to say something. But this equation 2 is quite interesting because we try to minimize both the deterministic error with respect to theta and the stochastic error, SSR, or something like, something like, because here we have a modification. But in any case, it reflects this statistical error because, yeah, structurally is an SSR, even though modified, even though we needed the modification because otherwise we don't have a convex problem. Okay, let me start with the easy example. Then with the example, we can repeat this, what I told you today, minimizing, let me open MATLAB, SSE. I will upload in my slide later. Let me open MATLAB. I will share in 1 second. In the meantime, let me look some slides. I have opened in MATLAB. No? Now we can understand better what I intend. Let me see if I don't have material. We can write again what I need. 1 second here. No, I can write for you what I need later. Okay, let me share MATLAB now. To work with MATLAB, I don't know if you probably not all students, well, let me share, worked with MATLAB. To start MATLAB, you have to click twice on the icon. This is at least in the Windows system is so. If you need to access MATLAB, I think the license is still available. If you send me an email, I will ask. Until last semester, yes, we had the license for the campus, but now, in accordance with the financial restrictions, I don't know if this semester we have, but I hope. Otherwise, we have to find a solution. But I think for the upcoming for this semester will work. Okay, if you click twice, you will very shortly because I don't have time to all the course of MATLAB, but I will tell you something now. We can see basically the path because we are working here in Windows, but of course in other operative systems looks a little bit different. You know, the path is in basically in any Windows software. Of course, the path can be changed. I don't need to tell you this because you know better than me. But very important that we have this region in the middle with some information depending of what we have in the file batch in the program and so on. Here can be used, this region here is in a command window. This means 1 plus 1, the answer is 2. And S is also in a variable, which you can see here in the workspace, together with different variable, which I set for my personal use. We can see here A and S, and the value of this variable or parameter, or a constant, in this case, in a constant, equal to. No? That we can intuitively understand that this in this panel, how we can use at least this part here, the command window in the middle, and here as diagnostic, let me say, the variables which is present in the kernel of the MATLAB. On the left part, we have the path, let me say. In accordance with the path, better to say, we have the folder. No? I think this is, I don't need to explain because of Windows. Very important now, look here. Here in this region here, we have M files. We will see, starting from after next week, that we can really generate very complex software. We will see in the particle swarm optimization methods. I will invite you really to attend the classes in the particle swarm optimization method, because I try to introduce a little bit some important concepts in the programming. While file, if file, while loop, if loop, for loop, and the particle swarm optimization methods are used in non-optimization, in non-convex optimization problem, excuse me. I'm a little bit already tired. M file means MATLAB file, because we will see that we have also Simulink file, which nevertheless a MATLAB file, but in the context of more graphical, structures. But anyway, in any case, it's graphical frame, but each graphical elements calls an M file. This means the kernel of MATLAB, M file. M means MATLAB. MATLAB means matrices laboratory. Look at this file here. It's exactly the example which I consider until now with this fitting problem. It's a little bit more didactic here, because the values are not real. The structure of the value, yes, but the value themselves is a little bit modified, because I need to clarify some aspect. In any case, look, the line 4, the line 1 I will not comment now. The line 4 is exactly the vector of the measurements. We have a 15 measurements in this case. Nevertheless, the unit reflects a little bit the real measurement, but the sequence is an artificial sequence, in order to be able to clarify some concept and so on. This apostrophe means instead of a row, we have a column. Apostrophe is transposition. The semicolon here is there, is a quite passive, totally passive, not but command, means basically don't print these values in the command window. We don't have here, because in this case, probably my idea was to look at the value when I run the software. The second line, the line number 6, is the exploration variable I. Remember the current x in our case was x, but I told you that in practically was in a current. No? Phi is the output, let me say, or the corresponding value with respect to I, the line number 6, or better to say with respect to the exploration vector. In this case, we have a row vector. I is a row vector. It's intuitive. No? It's exactly as we write in a row vector. In phi, lines 4, we have a column vector because of this apostrophe, which indicates or it represents in MATLAB the transposition. I know I think that you know what is net transposition. Eh? Everything which is column becomes row. Everything which is row becomes column. The line 8 is exactly the exploration matrix. 1 minute to explain this, and then we will see the line 10. Again, the goal is to show you how I can minimize SSE. Easy example. SSE, not R square, not S square adjusted. SSE. And then I don't know if I have time today. Next week we will see we can optimize R square adjusted, but a square, the meaning of a square adjusted is related to the minimization of theta, which we will do today, and together with n. This is a little bit more complicated, but not only complicated in sense of the calculations, but yeah, they are connected because the problem is not convex. When I introduce n in the optimization problem, the problem is not convex. Let me explain here. The matrix X phi. Why the matrix X phi at this structure here? Because I is a row vector. I put an apostrophe because I need a column vector. I show you in 1 second why. Then I put dot because each dot means each element of the row column vector must be up to n. Where this comes from, and this excuse me, this can be done also for the vector, the column vector up to n minus 1. N is equal 5 in our case. I didn't comment, I didn't put anything, but n is equal 5. Why that? Because it's fixed. At this moment, it's fixed. I would like to show you this case here, which is in this case extremely easy in the sense. I mean, n is fixed. We don't care about the optimization about n. Therefore, it's 5. Why? I don't know. I can put also a different value. Of course, change the dimension of the matrix X phi. In this case, it's X5 because recalls that n equals 5. I have to basically represent, it's a representation problem. Which one? Let me share. I have to represent this matrix X. We can see that we have a column which consists of the exploration vector, x1, x2, xm. We have m measurement. Each element up to n equals 5 in our case, fixed. You can change, but if you change the dimension of the matrices. Change the number of columns. The number of rows is fixed by m, the measurements, the points which I consider. The number of columns depends of the order. It's fixed at the moment, don't care about that. If I include in the optimization problem n, this means the number of coefficients, the problem becomes complex, extremely. We will see next week, we don't have time today. Let me conclude this. But I can do the same for each column of my exploration variable up to n-1, n-2, until up to 0, in which we have the column of ones. I don't know if it's this representation, just a representation, just a representation. I don't know if it's clear that, let me go to MATLAB, why the structure of this exploration matrix in MATLAB consists of this form here. We can recognize here is the column up to 1. We don't need dot because it's up to 1. Here I need the dot, for instance, because it's up to 2, and each element must be up to 2. You know that a vector square doesn't mean, I mean, we can define the vector square. This is the definition. The vector square in our context is each element square, if you want. And here we have a column. We can see the column because we have this one because MATLAB interprets this 1,15 as a row of ones, 15 ones, because 15 and the number of measurement. Look at the line 10. The line 10 is the solution. The line 10 is the copy of, let me share, of this solution here. You remember in MATLAB, inverse of x5 apostrophe, transposition, multiply x, inverse, up to -1. We reflected this separability concept. If we want to include also the optimization of n, I cannot separate. But if n is fixed, I can separate. Multiply x transpose, x5 apostrophe, multiply y. In our case, y is phi. Phi is already in a column in our representation. Of course, if let me share. If I don't have this apostrophe here, excuse me if I insist on MATLAB, but I know that not all students know MATLAB. If I don't have this apostrophe, I need an apostrophe here. Feed apostrophe, if I don't have, because y, also in according to our notation in the lecture, is in a column. Okay, this is the solution already. We don't need to go ahead, but is the solution in which sense? It's the parameters which compresses or compress the parameters, the information of the regressor. The regressor is totally defined with its parameters. But of course, then I need, if you want to visualize the solution, I need to represent the solution in order to have a better feeling. This means I will define a vector between -1, -5, and 5 with the resolution 0,02. This is a way to define a vector in MATLAB. Look a little bit also now at the solution. I don't have time to explain these technical aspects. Why it's between -1, -5 and 5? Because we can see that in the domain, the measurements span between -5 and 5. 0,02 is arbitrary, just in a good resolution to represent graphically. But the solution, again, is in 10. I show you, I have a few minutes, but I would like to conclude with this software. Next week, we do some complicated situation. The line 14 probably clarified a little bit better, because the line 14 is a representation of the function, the blue line, the lecture. And we can see that we have θ1, we have a vector theta, which consists of 6 parameters, or the polynomial or the phi at 6 parameters. And we can see that the first parameter will multiply the vector, which each element, dot means each up to 5, plus the second parameter, which multiply the vector with each element up to 4. I build basically the polynomial with the line 14, 6 parameters. And then I can plot phi c over or the versus IC. I put in a grid. I hold on in order to compare with the measurements. With the measurement. I plot also the phi measured versus I. And I characterize this point with a red star, just to have a visualization of the results. Here, at this moment, I didn't consider R square and not R square adjusted. We will see next week. In a more complex problem, in which we try to optimize also n. Here n is given, 5. But why 5? This is the problem which you attack next week. Let me run now the solution, then I recap what we have seen today and what we will see next week, even though I already told you. If I run, of course, running in Simulink in MATLAB means change the folder, because we can see that we have another folder here, no? With other things. Look, in the command window, we have the results of data. Why that? Because we don't have here a semicolon. This is the reason. If I put here a semicolon, I don't see the result in the command workspace, but they are nevertheless in the kernel. They are nevertheless, how possible to say, we can see data here. We can see here data. We can see here. Do you see data here on the right in the workspace? But you don't see in if I put semicolon in the command window. But very often it's more comfortable to see the value in the command window. Yeah, let me. It seems to be everything 0, but it's not. We have a 0 nevertheless. Let me see. Format long means that I will consider the full representation of my value. Let me show you what I intend. Now we can see that we have many zeros. This is the didactical expression. You remember I told you that the values are a little bit artificial, because I consider it an odd function. If you look phi, the value are artificial because they are symmetric with respect to 0. 4 minus 4, 5,5 minus 5 minus 5, 4,5, excuse me. We can see here 4,7 and minus 4,0 because using an odd regressor, all even element of the regressor are 0. Mathematically, really cannot be. Really, we have no odd, no even function. Do you remember also in math, sometimes in order to complete the analysis of odd and even functions, we say could be also not odd, not even. This is the real case. I put so in order to notice this. No? The solution is this, basically. Compress what? Compress, let me show you now the graphical solution. What we see here, compress. This is not the solution, it's the graphical expression of the solution. If you want the results, because our goal is to have information between current 0 in this case. Let me, I don't have. No, I run too much. Let me close. Let me draw. Excuse me. Without mouse, it's difficult to manage the computer. 1 second. Mm. Now I have a problem too. Let me clear 1 second. Okay. Let me run. Without mouse, I made now. No. No. I changed a couple values, probably. Yeah. You can see here with the mouse, I have -3 instead of 0. No, because I made mistakes with the mouse. One second, I'm concluding. Oh no. This is the graphical solution. That the idea is with this solution, we can have information between current zero and current, I don't know, this current here, for any value of current in the sense. No? Because basically you have a regressor, of course, with the resolution 0,02. This must be, practically must be considered. I mean, I can reconstruct, I can have information thanks this analysis on all current between -5 and 5, but this is the resolution. But of course, I can improve the resolution. Okay, what we did now to conclude, and for a given n, and next week we remove this hypothesis, and we will see how we can proceed in a heuristic form, because the problem is not convex. And then after next week, we will start with particle optimization method, an interesting method which can be used to realize in an automatic isn't a solver, no? Automatic way or the method to calculate, or to try to calculate possible solutions in the concept of not convex optimization problem. Because if the problem is not convex, we have more than one solution. This means here, for a given n, we will find with the line 10, the theta, the parameter of the regressor, which minimize SSE, Let me see. Yeah, I think this means we try with this approach to minimize the deterministic error, no? Because SSE is related to the deterministic error, as I told you, because we have the elements that is more deterministic, the model, the measurement too, even though the measurements are also affected by stochastic error, but they selves are deterministic. I mean, is the error between what I measure and what I am trying to represent. And we will see if I include n, the problem is very well posed, trying to minimizing SSR. This means at the end, we have the minimization of both possible error, SSE, deterministic, and SSR, stochastic. Do you remember at the beginning? Let me show you the slide again. I'm concluding. At the beginning, I started considering an abstract form that we have two possible errors, statistical error and deterministic one. And then during this explanation, a little bit fast, yeah, we are considering basically this possible structure. This is the model, basically SST equal SSR plus SSE, which works for M much, much larger than M1. What is the meaning much larger is clear, is not exactly sharp defined. No? But intuitively we can understand. We have to build a statistic, consistent statistic, in which we have basically with the data are represented or reflected SST, the sum of these two possible errors, even though, of course, and the separation and the total separation is not possible. It's just a model. But we have, let me say, in a linear combination between stochastic and deterministic errors. And the idea is to minimize both in order to have a suitable and optimal representation. Next week, we will see what change introducing n, excuse me. I will try heuristically to show you which kind of problem we have. Then in the second part, I will introduce quickly the problem of a fitting, considering another family of regressor, trigonometric regressor, because probably you are more familiar with Fourier analysis and so on, but we can consider in your project, we did different project with exponential function and so on, and we will complete in this sense this chapter related to the frame of the optimization problems. And after next week, we will start with particle optimization problem, which we will go in depth on the program. Isn't a solver, no? In some literature, we say that optimization is the theory of the solvers. I have time just to introduce one solver, but this is enough to understand the concept. I don't know, it could be that we will see also some aspects related to the tangent method that I would, this in any case. But more in depth, I don't know if I can do the Raphson, Newton, and so on. But also this PSO reflect, in any case, this gradient methods and so on. Gradient, we will numerically we will look when the gradient is going to zero to find the possible optimization optimal points. It's the derivative to zero again, the concept, which aim the solver, the methods. Okay, I will upload this file here. Next week we will upload this M file, also different M files. And then I have a material related to the trigonometric regressors. It is enough for me to show you at least two regressors, two issues with two regressors, even though each regressor are different issues. But anyway, I don't have time to. Theoretically, the regressors is infinite. I mean, I can mix also, no? Exponential function with trigonometric, I can do. Of course, in this case, we end up in always not convex problem, because the constraint is a particular, you cannot really separate what I know with what I don't know. If I have a question, I'm here for you. Otherwise, we will see next week more or less at the same time. Today is a little bit strange because I'm alone in the room, but it's okay. It is okay, no? Because it's allowed to attend the class also from home. No? It's in complementary is allowed. Questions? If no, we go ahead and then I will also write for you points by points the condition, the aspect of your projects, but a little bit early, in a couple of weeks. I can communicate officially per my study, even though I already told you what is the idea of the projects. But we know each other also from other courses. It's more or less the same. We will see next week. Thank you for your attention. I hope it was not so boring, the lecture.